Okay, so again, thanks Dirk. My name is Matt Dancho. I am the founder of Business Science, and what we do is open source software for business and financial analysis. So with me here today, Davis, you want to just wave your hand? Okay, he's our software engineer, and what I'll be talking about is new tools for performing financial analysis within the Tidy ecosystem. Okay. So goals today, I just want to discuss just briefly the existing financial analysis landscape. You guys already know it, but I do want to touch on that really quickly. And then I will also talk about or try to answer the question, why TidyQuant? And then what we'll talk about is the 5 core TQ functions. And then last, we'll show off TidyQuant with data science at scale, one of the main benefits. All right, so the financial analysis landscape. There's a bunch of packages. We love them all. XTS, Zoo for time series, QuantMod and TTR, getting data, manipulating data, and then performance analytics for return metrics. These are well-developed packages, and they've got a ton of useful functions in them, all for data transformation and financial analysis. We also have the Tidyverse, a collection of packages that all have a well-developed infrastructure for a data science workflow. They are a little bit different than the XTS system, and we'll talk about that next. So we've got the XTS system, two systems, XTS and Tidyverse, each have benefits, okay? So you've got XTS, it's built for speed, it's matrix-based, it deals with the wide format because it can only handle numeric columns, but it is fast, and we all know that. Tidyverse, on the other side. So we've got this thing that deals with data frames, all right? It's a little bit slower, but it's flexible, and it's built for scale. It can handle any types of data in the columns, which allows us to do work with what's called the long format data frame. And basically what you're doing is it allows you to group by subsets of the data and apply functions to those groups. That's the main advantage, or one of the main advantages. So the theory behind TidyQuant, what we're trying to do and what we've done is integrated the Tidyverse with the financial analysis packages. We're trying to get the best of both worlds. So user input is in data frames, input and output. Internally, what we're doing is converting to the XTS system, applying those functions, and then what we're getting is matrix speed with data frame flexibility and ultimately Tidyverse scalability. Okay, so there's 5 core functions. There's TQ get, which is to get data. There's TQ transmute and TQ mutate, and what this does is allow you to apply those QuantMod, TTR functions, such as like period returns or simple moving average or Bollinger Bands, and you can apply this right to the data. We've got TQ portfolio, which is for aggregating portfolios, and then TQ performance, which is for the performance analytics functions. So if you notice, it's got the import, transform, and model, the very same type of workflow that you have in the Tidyverse. Okay, so the key benefit of TidyQuant is scalability. Going from 1 asset to 500 assets is not that much different. So we've got just 1 asset. We'll take the stock ticker Apple. Just put it into TQ get, and out comes your 10 years of stock data, very similar to QuantMod get symbols. Going to 500 assets is where you get your advantage. So we have a handy little helper function called TQ index. We pass it S&P 500. That gets us the S&P 500 stocks. It's just a data frame of stocks. You pipe that into TQ get, you get those stocks converted into all of the daily historical prices. And then if you tack on an additional group by and group it by the symbol, you're ready to do the long analysis that I was talking about, subsetting and applying functions. All right, so what did we do with S&P 500, what did we do with the scalability? We analyzed the S&P 500, okay? So taking that same code that was on that last slide, we added 1 additional line of code, TQ transmute, and applied QuantMod period returns. We got the returns. And then what we did was grouped them by stock symbol and basically just plotted or calculated the mean and the standard deviation. What this allowed us to do is get us a nice graph that really essentially lets us gives us insight. It shows an inverse relationship between the volatility and the returns. And this is something that we can use to make meaningful strategic decisions when it comes to investments. We can extend that analysis very easily. So I talked about grouping by symbol. You can also group by symbol and year, so multiple combinations. I just piped that right into ggplot, and now we can compare the high performers, and we can realize that, oh, not all high performers are created equal. So don't just go by the last graph, go by this graph too. Okay, and then this is just to show you kind of a different example of scalability. We can also work with portfolios. So this is just analyzing the multiple portfolios, and that's another aspect of TidyQuant. Last but certainly not least, we've got the future coming up. I've heard a lot of questions from individuals. We're focusing on speed, connectivity, data sources, machine learning, AI, and also flying cars. God, that was a mouthful. All right, we're not really focusing on flying cars. Last but certainly not least, standing on shoulders. Without several of these people in this audience, and also others at our studio, we certainly would not be here talking about TidyQuant today. So thank you guys very much. All right, now I can breathe.
So hello everyone, my name is Leonardo Silvestri. I'm the author of ZTSDB, which is actually a time series database management system, has a tight integration with R. So the main concepts of ZTSDB, it's basically a fast, small, so it's about 22,000 lines of code, fairly compact, multi-user, NoSQL, column store database management system, and it's also free software. The query and manipulation language is a subset of R. It's got a tight integration with R, a coherent and rich representation of time. It's able to do streaming transformations, and it's got a seamless connectivity with other ZTSDB instances. So query language, mostly it's a subset of R. It implements the same array, matrices, lists. Additionally, of course, it implements a time series type, ZTS. All these can be persisted and made persistent to disk. These time series have basically the usual array functionality. It can do about what you can do with usual arrays in R. Additionally, ZTSDB has a richer set of temporal types than R, an escape operator and a pass-by reference operator that's necessary to avoid the copies of really large time series. The integration with R, ZTSDB queries can be written unquoted inside an R session. So here's an example. You load the relevant libraries, create a connection C1 to a remote ZTSDB instance, and using the query operator, that question mark, everything that's on the right will actually be sent over and evaluated on the remote instance. If you specify the ++, which is the escape operator, that will actually make all that expression after the ++ operator be evaluated locally inside the R session, bundled as part of the query, sent over to the remote instance, and that will come back, obviously the result will come back in R. And there's a fairly similar mapping of types between ZTSDB and R. So time, it's basically a time since epoch. It's got nanosecond precision, time zone awareness. There's 4 types: point in time, duration in nanoseconds, an interval. So basically 2 point in times, a start and an end. And it's possible also to specify if that start and end actually belongs to the interval. So it's possible to have open intervals. And finally, a period. That's basically a duration with a calendar, a human concept, such as a day, a year, a month, or a combination of these. It's got specialized functions to handle time. Here I'm showing just a quick example. It's a function called density. It's available on the website in the examples. Basically, it's composed of those lower level primitives that are available in ZTSDB, like align and sec. And all it does is count the number of observations for the given duration. So here, I'm having minutes, hours, and days. we're assigning the result of the queries to these variables in R. And then these variables in R are XTS time series, and they are available for plotting, for example. So the data here is irrelevant. It's simulated data. The point I'd like to make is show a little bit the workflow that's possible between R and ZTSDB, where R and ZTSDB can share the task of bringing the relevant data. Streaming transformations, they're timer-based. The idea here is to make live time series, derived time series from existing time series that are also live. So make a transformation of time series. So typically, they could be aggregations, but actually it's possible to write arbitrary code, so they can be much more complicated than simple aggregations. Finally, connectivity. ZTSDB instances are always both client and server. They have a fairly symmetrical way of exchanging data, on pushing and pulling data. So it's possible to come up with some fairly flexible architectures. So here I'm just presenting one architecture. Here's a set of collectors that are actually ZTSDB instances. They're being fed a stream of data. They are potentially creating derived time series from that raw data. And they will actually push that data to database 1 and database 2. So all these, the collectors and these databases are actually ZTSDB instances. And then it's possible to have an arbitrary number of R sessions query database 1 and database 2. So you also could query directly the collectors. So that's it. I hope that has sparked a little bit of curiosity for ZTSDB, and I thank you very much for your attention.